Hello everyone, my name is Proctor and today we're going to talk about statistical modeling. We have 6 tasks to go over. The first 4, we're going to be using this heart data set, which has our age in days, our gender, 1 represents male, 2 represents female, our height in centimeters, and our weight in kilograms. And so our first one is for our hypothesis task. And so we're just going to go over that what is outputted. We have our t-statistic with the value of negative 41.6216 and a p-value of 0. We have our box plot of the weights by our gender. And so 1 represents male, 2 represents female. And so here we're going to reject the null hypothesis because there is a significant difference in mean weight between males and females. So let's talk about our report, just quickly go over it. And so here we're examining whether there is a significant difference in the average weight between men and women using our heart data set. And so we're focusing on comparing the weights of males and females to see if gender influences weight. And so the data is analyzed and we separate the weights into 2 groups based on the gender. We have an independent samples t-test, which is used to determine if there is a significant difference between the mean weights of the 2 groups. And our t-test results show a t-statistic of negative 41.62 and a p-value of 0, which indicates a difference, a very significant difference between the weights of men and women. Our box plot also supports this by showing distinct differences in the weight distributions between the 2 genders, with men generally having higher or more varied weights than women. And so we conclude that men and women in this data set have significant different average weights. Time to go over our correlation coefficient task. And so let's look at what the code outputs. So our correlation coefficient between height and weight is 0.2910. We have a p-value of 0. Our scatter plot, here we have a scatter plot of height versus weight. Each dot represents a person, and then we have our linear fit with an upward trend. Let's go over our report. And so here we're aiming to find the relationship between height and weight using data from the heart dataset. After extracting the relevant data, we calculate the Pearson correlation coefficient, which measures how strongly height and weight are related. The coefficient is 0.2910, which indicates a weak positive relationship, and this means that as height increases, weight tends to increase slightly. Our p-value is 0, and this shows that this relationship is statistically significant, meaning it's unlikely to be due by chance. Our scatter plot with a linear regression line also is used to visually confirm this weak relationship. However, the scattered data point suggests that height alone is not a strong predictor of weight, implying that there must be other factors that play a more significant role. And so in conclusion, there is a statistically significant relationship between height and weight. It's very weak, and other factors should be considered for a better understanding of what influences weights. Now let's talk about our linear regression model task. By first looking at what is outputted by our Python code. Our ordinary layered squares regression results show that the r squared has a value of 0.085, and looking at our notes, the condition number is large, which indicates that there are strong multicollinearity or numerical problems. Our scatter plot, which shows our height versus weight with a fitted regression line, is displayed here. And then we also display our residuals versus our fitted values. In our residuals plot here, we output that the pagan test indicates heteroscedasticity because the p-value is less than 0.05, and so we should consider addressing it. So let's go over our report really quick. And so our report is attempting to create a linear regression model and that predicts a person's weights based on their height. And so the model found that height can only explain about 8.5% of the variation in weight. Because this is indicated by our r squared value. And although the relationship between height and weight was statistically significant with a p-value of 0, the weak correlation suggests that height alone is not a strong predictor of weight. And our scatter plot showed that while there is a slight upward trend, the data points are widely scattered, which indicates that the model does not accurately predict weight. Further analysis revealed issues with the model. In this case, heteroscedasticity, which means the variability in weight predictions changes across different heights. And this problem was confirmed by a statistical test, which showed that a very low p-value indicates that the assumption of consistent variance was violated. And this means that the model's predictions could be unreliable. And so to improve this model, adjustments like data transformation of the dependent variable or using more robust methods could be necessary. Overall, while the model found a statistically significant link between height and weight, the relationship is weak, and the model's reliability is compromised due to the issues that we had found. So now time to talk about our multiple regression model, but going over what is outputted by the Python code. So we have our OLS regression results with an R-squared of 0.091. From our notes, the condition number is large, and this might indicate that there are strong multicollinearity or numerical problems. We have our height versus weight with fitted regression line plot, and then we have our residuals plot for our residuals versus our fitted values. Outputted here. Our Brewis-Pagan test indicates heteroscedasticity because it has a p-value that's less than 0.05, so we should consider addressing it. We have our VIF values displayed here, and so multicollinearity was detected because our VIF is greater than 10, so we should consider addressing this. So let's first talk about our study really quickly. And so we're aiming to improve the weight prediction model by adding age alongside height as predictors. And so our results showed that both height and age are statistically significant factors in predicting weight, but they only account for about 9.1% of the variation in weight, as indicated by our very small R-squared value. And this suggests that other important factors influence weight were not included in the model. And so the model also showed signs of multicollinearity, where the independent variables, the height and the weight, might be too closely related, which makes it difficult to accurately determine the effect of each one on weight. And this issue can lead to unreliable predictions. Additionally, the model exhibited heteroscedasticity, meaning that the variability in the errors changed across different levels of the predictors, which violates a key assumption of the linear regression and can lead to biased results. So in conclusion, while height and age are factors in predicting weight, they explain only a very small portion of it, and issues like multicollinearity and heteroscedasticity make the model less reliable. And so to improve the model, it's necessary to explore additional predictors, make data transformations, or use different modeling techniques to address these issues that we found. So now let's talk about our solutions task by first looking at what's outputted by the code. So in our OLS regression results, we have an R-squared value of 0.175. Our notes say that the condition number is large, and so this indicates that there are strong multicollinearity or other numerical problems. We have our residuals versus our fitted values displayed here, and then we have outputted, we see that there are no heteroscedasticity detected in our data. So let's go over our report. And so here we're using our data set, our USA housing data set. We're mainly using the variables of price, square footage of living, and I believe those are really the only two that we're using here. If we go back to our report, We're focusing on creating a simple linear regression model to predict house prices based on square footage of living space using this USA housing data set. And so our goal is to check if the model met the key assumptions of linear regression, particularly whether the errors in predictions were consistent. And so our model found that square footage could explain about 17.5% of the variability in house prices, which means other factors also play a significant role in determining prices. The model showed a positive relationship between square footage and price, with the prices increasing about $255 for every additional square footage. Our analysis included checking the residuals to see if they were randomly distributed, which indicates no issues with homoscedasticity. And so our results confirm that the model met this assumption, and there's no signs of inconsistency in the errors. If the model did show signs of heteroscedasticity, a log transformation of the price variable could have been considered to correct it. However, since there weren't any issues found, this adjustment was not necessary. So in conclusion, the model reliability predicted house prices based on square footage under the specific conditions tested. However, the very small R-squared value suggests that future models could include additional factors to better explain the variability in house prices. Our study highlights the importance of checking and confirming assumptions to ensure accurate and reliable model predictions. So now let's talk about our final task, our non-linear model. So let's look at the results that are outputted here. We have our linear model summary with the R-squared value of 0.175. We have our nonlinear model with an output of 0.192. Both from these notes, the condition number is large for both, and this indicates that there are strong multicollinearity or other numerical problems within this data. Our linear model mean squared error is very large as well for our nonlinear model. We have our linear versus nonlinear model fit. The red line indicates the linear fit, the green lines indicate the nonlinear fit, and then we have our actual data points, our price, and our living spaces. We have our residuals versus our fitted values for our nonlinear model represented here. And so let's quickly go over our report. And so our study is focused on predicting house prices based on square footage using both linear and nonlinear regression models. Our linear model explains only about 17.5% of the variations in house prices. This indicates that it missed capturing much of what affects prices. And so to improve this, we added a quadratic squared term for square footage to create a nonlinear model. And this nonlinear model did a better job, and it increased the explained variation to 19.2% and showed more accurate predictions, especially for bigger homes where prices tend to rise more quickly. And so our visual and residual analysis confirmed that the nonlinear model was a better fit for the data. It shows fewer patterns in the residuals and more closely follows the actual price trends, particularly for homes with more living space. In conclusion, adding the quadratic term significantly improved the model's ability to predict house prices, highlighting that the relationship between square footage and price is more complex than a simple straight line. And this improved accuracy suggests that considering nonlinear relationships is important when modeling real-world data. Thank you for listening. That is all.